Now let us summarize the given properties, and these are for function values. If we have the add property of linear functions, suppose that we have a linear function f, then adding a constant to x results in adding a constant to the corresponding x value or f of x value. So if you add a constant to the x values, such as in what we have seen so far, okay, it will result in adding a constant to the corresponding f of x value. So if f of x is equal to ax plus b, and x of 2 is equal to c plus x1, then f of x2 is equal to a times c plus f of x1. Okay? We have the multiply property of power functions. In this multiply property, now if your f is a power functions, then multiplying x by a constant results in multiplying the corresponding f of x value by another constant. So multiplying x by a constant results in multiplying the corresponding f of x value by a constant also. So if we have f of x is equal to axb, or ax raised to b, and x sub 2 is equal to cx sub 1, then f of x sub 2 is equal to c raised to b times f of x1. Now we have the add multiply property of exponential functions. So this is exclusive for exponential functions. If f is an exponential function, adding a constant to x results in, so if you add a constant to x, it results in multiplying the corresponding f of x value by constant also. So if f of x is equal to ab raised to x, and x sub 2 is equal to c plus x1, then f of x2 is equal to b raised to c times f of x sub 1. Constant second difference property, that's for the quadratic functions. So if f is a quadratic function, f of x is equal to ax squared plus bx plus c, and the x values are spaced d units apart. So if they are spaced d units apart, then the second differences between the f of x values are constant, and the second differences are constant and is equal to 280 square, and 280 square is just 2 times the coefficient of the quadratic term times the difference between the previous and the succeeding x values, so d, and then square it, so d square. Okay? This is not actually 3. It has, this is the coefficient of the leading, or the leading coefficient of the quadratic function. Okay. Now let's have some examples. Example number 1. Identify the pattern in the following function values and the kind of function that has this pattern. So let us investigate the table. Our table is in here, okay? There seems to be an add on the left side, because we have plus 1 here, plus 1, another plus 1. On the second values, the f of x values, we have 5 to 7, 7 to 11, 11 to 17, and 17 to 25. Now let's see what kind of pattern do these values represent. So we have plus 2 here. We have plus 2. Now we have plus 4. We have plus 6. And we have plus 8. Okay. Now we can see that if we are to get the second differences, then we will have plus 2, plus 2, plus 2. Note we don't have the add property. No add property. What else? No add multiply. So certainly not. No add multiply. No multiply. But we do have the second differences. Because when we took the second differences, we got a constant second difference for all the values of f of x. Therefore, this is most likely belonging to the quadratic function group. So this is a quadratic function pattern. Okay, so this is a quadratic function pattern. Example number 2. If function f has values f of 5 is equal to 12 and f of 10 is equal to 18, find f of 20 if f is a linear function. So what does a linear function has to do with the patterns? A linear function must have an add pattern on the tables, right? So this is add. And if we have a power function, then we have multiply. So multiply. If we have an exponential function, this is add multiply. So let us create a table of values for our okay. Let's create a table, okay? But I don't like the color. Okay. So let's have this. Okay. One, two, 3, 4. This would be our x values. This is our f of x values. Okay, we are given f of 5 and f of 10 and f of 20. So if we have a linear function, then definitely this will be add. So if we have 5 and we have f of 10, so if our x is 5, then we have a corresponding 12 value for f of x. If our x is 10, then we have a corresponding 18 for the value of f of x. And if our x is 20, then we have, this is unknown. So if our 20 is the x, if x is 20, then we have an unknown, and then we're going to get the f of 20 here if it's add. Of course, if it's add, then we should have a pattern which is adding for every x values. Then we could see an addition which is constant. So in here we could see that we have a constant of plus 5, okay, and plus 5. And on the second, on our left or on the right for the f of x values, this is actually a difference of 6. Okay, so we have plus 6 here, and if we apply that here, then definitely our next f of x value would be 24. Okay, and the next f of x value for our x is equal to 20 would be 30. Am I correct? Because we have plus 6 for every f of x values. Okay, therefore we would have a graph that looks like this on the right of the given table. So at x is equal to 5, our f of x is equal to 12. If our x is 10, then it's 18. If our x is 15, we have 24. And if our x is equal to 20, then we have y, or f of x, is equal to 30. So this will look like the one here on the right. So this image here. Okay? So what if it is a power function? So note that if it's a power function, we have to have a different approach. So we are going to form another observation, another approach for this table given. And remember, we are only given the f of 5 and f of 10. So we will erase everything in here except our f of or our x is equal to 20. So we don't need this anymore. Okay. Now if our function is a power function, it's multiply, right? Therefore, we should have a multiply pattern. In this case, we see that we have a pattern going to the x values, and the previous to the succeeding gives us times 2, right? And here the corresponding x value would have a value multiplied by 2, so it became 20. Now if it's the pattern we're assuming, then to our right we have 12 to 18, then that would be a ratio of, if we divide both by 6, then we will have a ratio of 3:2, so it's 1.5. So we could actually form a conclusion that it is multiplied by 1.5, and this one is also should be multiplied by 1.5. Therefore, our f of 20 should be 18 times 1.5. We have our calculator here. 18 times 1.5, so 18 times 1.5 is equal to 27. So our f of 20 should be equal to 27. Okay, so that's for the power function. So notice how the patterns change, the f of x values change with respect to whether the given table is assumed to be a linear function, or is assumed to be a power function, or is assumed to be an exponential function. So if our function is a power function, then our f of 20 is definitely 27. Okay. What if our function is assumed to be an exponential function? So we're going to erase all of the given, all of the given values here, and we will start with forming the f of x for x is equal to 20. So we're going to erase 27 now. And if it's an exponential function, we should see the pattern of add multiply. So therefore, we have a pattern of adding plus 5 here. So we will add 5. So we should also add 5 here and 5 here. So we have plus 5 here and plus 5. So filling this, what do you call this, empty cell here. So this would be 15 again. And 20. And for the f of x values, we should see a multiplication value. So 12 to 18 is multiplied by, again, 1.5. So this should be multiplied by 1.5. And of course, this one should also be multiplied by 1.5. So whatever is the value here should be multiplied by 1.5 to get the f of 20. Okay, so 18 times 1.5. We have seen it a while ago, and it's equal to 27. Now 27 times 1.5. So we have the value here times 1.5. That gives us 40.5. So we now have 40.5. Okay, so take note that the f of x values again change as we also deliberately change the kind of function that is assumed to be following this given table for x and f of x values. Okay, and if it's an exponential function, then it would most likely look like the graph on the right. Okay, and that gives us our patterns based on the given assumption and based on the given values for x and f of x.